Welcome to AI Frontiers, your source for cutting-edge developments in artificial intelligence research. Today we're exploring recent advances in machine learning research that are pushing the boundaries of what's possible in AI systems. The papers we'll be discussing represent significant contributions to the field, showcasing innovative approaches and groundbreaking results that may shape the future trajectory of artificial intelligence. Machine learning enables computers to learn patterns from data and improve their performance through experience without explicit programming. This technology forms the foundation for numerous systems we interact with daily, from recommendation engines and voice assistants to autonomous vehicles and medical diagnostic tools. The field spans multiple approaches, including supervised and unsupervised learning, reinforcement learning, and deep learning architectures. Drawing from mathematics, statistics, neuroscience, and other disciplines, machine learning researchers continue to develop new approaches for extracting insights from data. Recent years have seen remarkable progress in large language models, diffusion models for generation, reinforcement learning algorithms, and graph neural networks, enabling AI systems to generate realistic content, play complex games at superhuman levels, and solve increasingly challenging real-world problems. Our first major research theme focuses on representation learning beyond traditional metrics. Traditionally, the quality of learned representations has been evaluated primarily through performance on downstream tasks. However, researchers are now recognizing the limitations of this approach. Plakoras and colleagues propose a unified framework for evaluating representations that considers additional properties such as equivariance, invariance, and disentanglement, crucial aspects often overlooked by traditional metrics. Naumann and colleagues introduce methods to make Wasserstein distances more explainable, allowing researchers to attribute distances to specific data components or features, enhancing interpretability. Zhang and colleagues explore how diffusion models can be leveraged for semantic embedding representations, demonstrating that these models can excel at learning discriminative representations that capture semantic meaning across different levels of noise. A key finding across these works is that models with similar downstream performance can behave substantially differently in terms of their internal representations, suggesting fundamentally different underlying mechanisms. The second dominant theme we observe is efficient, large-scale model deployment. As machine learning models grow in size and complexity, deploying them efficiently becomes increasingly challenging. Zhou and colleagues introduce FloE, a system for on-the-fly mixture of experts, inference on memory-constrained devices. By compressing expert parameters and employing sparse prediction techniques, they achieve significant acceleration without sacrificing performance. Similarly, Duanmu and colleagues propose mixed precision quantization for mixture of experts, of models, applying different quantization precisions based on component sensitivity to balance computational efficiency with model accuracy. These works reflect a broader trend toward making advanced machine learning models more accessible and deployable in resource-constrained environments. As models continue to grow in scale, hardware-aware machine learning approaches become increasingly critical for practical applications. Our third research theme addresses robustness and generalization under distribution shifts. Ensuring that machine learning models perform reliably when faced with data distributions different from their training data is a critical challenge. Sun and colleagues introduce a learnable random walk perspective for improving the generalization of graph neural networks when applied to unseen graph structures. Yi and colleagues tackle the problem of open set label shift, developing estimators for both source and target distributions when the target contains an additional out-of-distribution class. Their method enables classifier correction without retraining. Schumann and colleagues focus on adversarial robustness in trajectory prediction models, used in autonomous vehicles, proposing an approach that creates more realistic adversarial examples by perturbing both past and future states. These works highlight the growing recognition that real-world deployment of machine learning systems requires robustness to distribution shifts, particularly in critical domains like healthcare, transportation, and finance. The fourth significant theme is the integration of symbolic methods with neural networks. Researchers are increasingly combining the strengths of neural networks with symbolic reasoning approaches to create hybrid systems that benefit from both data-driven learning and explicit knowledge representation. Lee and colleagues present UniSymNet, which unifies nonlinear binary operators into nested unary operators, and uses a transformer model to guide structural selection in symbolic regression. Bartle and colleagues explored differentiable fuzzy neural networks for recommender systems, integrating fuzzy logic with neural networks to create more transparent and interpretable recommendations. Zhu and colleagues demonstrate the power of combining knowledge-guided approaches with data-driven techniques in discovering partial differential equations, training a generative model on existing equations to facilitate the discovery of new ones from data. This theme reflects a recognition that purely data-driven approaches may have limitations in terms of interpretability, generalization, and data efficiency, which can be addressed by incorporating symbolic reasoning and domain knowledge. Several groundbreaking findings emerge from recent machine learning research that could shape the future direction of the field. Justin and colleagues systematically evaluated 27 frontier large language models on 8 diverse biology benchmarks, finding that top models now perform twice as well as expert virologists on the challenging virology capabilities test. Several models match or exceed expert-level performance on other complex benchmarks, suggesting these models could serve as powerful tools for accelerating biologic discovery. Pakoras and colleagues introduced a standardized protocol to quantify various attributes of model representations, revealing that models with similar downstream performance can behave substantially differently regarding these attributes. Hasegawa and colleagues presented auto-tensor singular value thresholding, a 9-iterative framework for tensor denoise that automatically extracts significant components without requiring prior rank specification. Esways and colleagues identified specific attention heads that focus on shortcuts in text classification, making premature decisions that bypass contextual analysis. Solanki and colleagues provided the first former analysis of how differential privacy affects algorithmic collective action, establishing mathematical bounds on collective action success as a function of privacy parameters. Several common methodologies are prevalent in current machine learning research. Diffusion models have gained significant traction for generative tasks across various domains, offering high-quality sample generation with stable training dynamics, though they require multiple steps during sampling, making inference computationally expensive. Transformer architectures continue to dominate across multiple domains, capturing long-range dependencies through self-attention mechanisms, though they can be data-hungry and computationally intensive for long sequences. Mixture of experts approaches have emerged as a way to scale model capacity without proportionally increasing computational costs, though they face challenges in implementation complexity and load balancing. Integration of large language models with traditional techniques leverages the rich world knowledge of LLMs while maintaining the efficiency of traditional approaches, though this introduces additional system complexity. Geometric deep learning extends traditional approaches to non-Euclidean domains like graphs and manifolds, capturing structural relationships in data that cannot be adequately represented in Euclidean space, though with increased mathematical complexity. Let's spotlight a particularly influential paper, Automated Learning of Semantic Embedding Representations for Diffusion Models, by Jiang and colleagues. This research addresses a significant gap. While diffusion models have demonstrated remarkable generative capabilities, their potential for representation learning has remained largely unexplored. The authors introduce a multi-level denoising autoencoder framework with a time-step-dependent encoder designed to acquire embedding representations along the denoising Markov chain. Their experimental results reveal several significant findings. First, the representations learned by their diffusion-based approach outperform state-of-the-art self-supervised learning methods on most benchmark tasks, achieving a 2.3% improvement in linear probing accuracy on ImageNet compared to previous methods. Second, they demonstrate that representations learned at different noise levels capture complementary semantic information. Early time steps preserve fine-grained details, while later time steps capture more abstract concepts. This work challenges the traditional division between generative and discriminative models, suggesting that the same underlying mechanisms can excel at both tasks. Our second spotlight paper is Crowding Out the Noise: Algorithmic Collective Action Under Differential Privacy by Solanki and colleagues. This research tackles the intersection of technical and social dimensions in AI development, specifically how privacy-preserving mechanisms affect the ability of user groups to collectively influence AI systems. The authors provide the first formal analysis of how differential privacy affects algorithmic collective action, establishing mathematical lower bounds on the success of collective action as a function of collective size and privacy parameters. Their findings reveal a fundamental tension. As privacy mechanisms become stronger, the ability of user groups to collectively influence system behavior diminishes, requiring larger collectives to achieve the same impact. This trade-off raises important questions about how to design systems that respect both individual privacy and collective agency, and who should make decisions about these trade-offs. The research has profound implications for the design of AI systems that balance privacy protection with user influence, potentially informing both technical implementations and policy decisions around AI governance. Our third spotlight paper is LLMs Outperform Experts on Challenging Biology Benchmarks by Justin and colleagues. This research systematically evaluates 27 frontier large language models on 8 diverse biology benchmarks, revealing dramatic improvements in biological capabilities. The results show that top models now perform twice as well as expert virologists on the Challenging Virology Capabilities test, with several models matching or exceeding expert-level performance on other complex benchmarks, including lab bench cloning scenarios and biology subsets of GPQA and WMDP. This breakthrough has profound implications for scientific research and education, suggesting that large language models could serve as powerful tools for accelerating biological discovery, aiding researchers in generating hypotheses, designing experiments, and interpreting results. The finding challenges conventional assumptions about the limitations of language models in specialized scientific domains, suggesting these models can acquire deep domain knowledge and reasoning capabilities that rival human experts, at least in certain evaluation contexts. Looking to the future, several promising research directions emerge from our analysis. First, developing unified frameworks that combine representation, learning, and generation could lead to more versatile and efficient AI systems. Second, creating more efficient deployment methods for resource-constrained environments will be crucial as models continue to grow in complexity. Third, enhancing robustness to distribution shifts and adversarial attacks remains essential for reliable real-world applications. Fourth, integration of symbolic reasoning with neural approaches could address current limitations in interpretability and data efficiency. Finally, addressing the tension between privacy, fairness, and collective agency will be critical for developing AI systems that serve diverse stakeholders while respecting individual rights. These directions reflect the field's ongoing evolution toward more capable, efficient, robust, interpretable, and responsible AI systems. This presentation was created through a synthesis of recent research papers using Anthropic's CLAUD-3-7-SONNET model. The text-to-speech narration was provided by DeepGram, while visual elements were generated using Google's image generation tools. All content has been reviewed by human experts for accuracy and relevance. While we strive for comprehensive coverage, some nuances or details from the original research may not be fully captured in this synthesized presentation. Our goal is to provide an accessible overview of cutting-edge research while maintaining technical accuracy and highlighting the most significant developments in the field. Thank you for joining us for this exploration of recent advances in machine learning research. We've examined dominant research themes, groundbreaking results, common methodologies, and spotlight papers that represent the cutting edge of the field. The rapid pace of innovation in machine learning continues to expand the capabilities of AI systems while raising important questions about their deployment, robustness, interpretability, and governance. By understanding these developments, we can better anticipate the future trajectory of artificial intelligence and its impact on society. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.